Okay, this is 10.3 homework help. First problem gives us a problem about limits. So they give us this graph here. I've made it a little bigger. The first one says we want to find the limit as x approaches -1 from the left. So -1 from the left, that is at 3. So we would say 3. Approaching -1 from the right also is approaching 3. So we'd say 3 there. Now the limit of the function as x approaches -1 overall then is 3, because from the left and the right we're approaching the same value. So we could say 3 there. Now the actual value of the function at -1 is 4, because you can see there's a dot there representing the value of the function at that point. So the value of the function doesn't have to be the same as the limit here, as you can see, okay? Because we're not actually talking about that point. We're talking about what the function is doing really, really close to that point. All right, so we can keep going with this then and do 1 from the left. 1 from the left is approaching -2. 1 from the right is approaching -1. And then 1 overall, the limit does not exist, and the reason why is because we have two different numbers here. So if you approach two different numbers from the left and the right, then the limit at that point does not exist. And then the limit as x approaches 3 of this function from the left and the right is the same, and that's 0. And then f of 3 is undefined because we have a hole there. So we would just say does not exist for that one as well. Okay, the next problem wants us to do the same thing, find some limits. So we have the limit as x approaches -3 from the left. -3 is right here. From the left, you can tell the function goes off to positive infinity, so I'd write I and f. -3 from the right, the function goes down to negative infinity, so I'd say negative I and f. Next one, limit as x approaches -1. -1 is right here. It looks like the function goes from the left and the right up to positive infinity, so I'd just write I and f. And then the limit as x approaches infinity of the function as you go out to the right looks like it approaches 2, and negative infinity looks like it approaches 3. Okay, another one of the same type of problems. As x approaches 2 from the left, so 2 is right here. From the left, the function is approaching 2. As it approaches 2 from the right, the function's approaching -2. As we go to 2 then, it's undefined. And then the limit of the function as we approach 0 is undefined, because it approaches two different values. And then g of 2 is what it wants, which is 1. Next problem is a little straightforward. It says what's the limit as x approaches 1. As x approaches 1 from the left, we're approaching 9. From the right, we're also approaching 9. Therefore, our answer is 9. Okay, the next problem wants us to sketch the following function and determine the values of a where the limit does not exist. So we have to sketch this. So let me do this real quick. It looks like this. Just graph this line and then just erase the rest of it. That's not less than -1. And graph this line and do the same thing. Erase the rest of it. It's not -1 to 1, and then graph the parabola and erase the rest of it. It's not greater than or equal to 1. And what you'll get is this, and you can tell the limits are defined then at -1 and 1, because those are the places where the function jumps. And when it's discontinuous like that, when it's got jump discontinuity, the limit does not exist. Okay, the next problem wants us to find the limit of this function as x approaches 8. If you were to multiply this all out, you'd have x to the 4th. We know what that generally looks like. It looks something like that. And so we're talking about a 0.8. We're talking about what is the value at that point. This has no discontinuity. This has no points that are undefined, which means that basically we can just plug 8 in. If we want to find the limit as x approaches 8, let's just evaluate the function at 8, because it's continuous here. So it's going to approach, at 8, x equals 8, it's going to approach the same number, and that number is the y value. So let's just plug it in, and if you do that for mine, you get 49,247. Just plug 8 in for x here, and evaluate this quantity right there. Same thing for the next one. We've got an absolute value function, which is shifted 8 units to the left. So if you went over to -8, you could graph this thing. It looks like this. Understand what happens when we stick in -8? Well, the function's approaching -8 from both sides. You can just substitute it in. You get 0. It's approaching 0 from both the left and the right. Next problem is the same thing. We can substitute in -3 here because it's not undefined at -3 and it has no discontinuity at -3. You can always graph this in the calculator if you want to see it, but there is no whatever this function looks like, there's no hole. The hole would be where the bottom's 0, so at least for mine anyway. And or there'd be an asymptote there. Either way, you know, if we were trying to find the limit at 5, that would be an issue because it's undefined at 5, so the function does have jump discontinuity there. Or removable discontinuity if this was a hole, as you learned about in Algebra 2. But for me, that's not an undefined value. I can stick that in, just substitute, and find the limit, which is negative 7.625. Now, if you happen to have a value that you're finding the limit and it's a 0 in the bottom of that in your numbers, then the limit does not exist. And we'll have to look at yours individually if that's the case, because it could be different if it's a hole or if it's a removable discontinuity. Because if it's a hole at negative 5, let's say over here, then you know, say you just have some kind of hole there, then the limit does exist. So if this factor cancels with a factor in the top, so if you can factor the top and get x minus 5 out of it and it cancels, then the limit would exist, and it would be what you get when you stick in that value. So, or I'm sorry, it would be the numbers that, you know, are right around next to it. So we'll have to look at yours if that's the case in class, obviously. Next one, once again for me, there's no hole here or vertical asymptote, therefore I can just substitute, and when I do, I get 0.0003199 about. Next one, same thing, I can substitute in 4 for t, because there's no places where this is undefined. A is just some number, so don't worry about it, just leave A as it is. When you substitute that in, 9 times 4 is 36, minus 2a times 4, which would be 8a, plus 7a. That just gives you 36 minus a. Okay, the next problem, problem 11, is a little harder. We can't, for mine anyway, I can't evaluate this by substitution because I get undefined. And actually both branches would be undefined because the bottom would be 0. So for a problem like this, we're going to have to use a calculator. So go ahead and graph this in the calculator. I've graphed mine already. And you can see it looks like the function is continuous from what you can tell, but we know it's not. We know at 7 it's undefined. In fact, we can check that by doing second calculate value at 7, and it gives us no y value because there isn't one. It's undefined there. But around it there is, you know, just to the left of 7, like 6.9, or just to the right of 7, like 7.1, we know that it's defined. So let's try like those values. Let's try 6. Let's do second calculate value at 6. And we get 1 over 13. Let's try one bigger than 7. Let's try 8 now. Second calculate value at 8, and we get 1 over 15. So it's not hard to see that in between those would be 1 over 14. So we can use 1 over 14 as our value for the limit. Okay, this next problem is tricky. I'm going to take this first function. I want to know what happens when x goes to negative 6. So I'm going to factor this. I'm going to make it x minus 6, x plus 6. And then in the bottom, I have x plus 6, x plus 7 it factors into. So 2 of these cancel, and that's important because that's a hole. That means we at x equals negative 6, we have a hole, which is exactly the point they're asking me to find the limit at, which at holes the limits exist because whatever the function does at that point, it looks something like this. You know, we can find a point right near that on either side, and it will work. Or we could, you know, since the function now is x minus 6 over x plus 7, this is the exact same function as the one they originally gave us, except for it doesn't have the hole. So now we can just plug in x equals negative 6, and we get negative 12 over 1. So my answer is negative 12. All right, the next part then, if you graph this function and you want to know what happens as x goes to negative infinity, to the left, it looks like it's approaching maybe 0, but what you remember is that when the exponent's the same, the top and the bottom, the horizontal asymptote is the ratio of the leading coefficients, so it's 1. That's on the formula sheet, and that's what we studied when we covered rational functions. But to find the horizontal asymptote, you take the ratio of the leading coefficients when the exponent's the same, which is just 1, which means this function is going to approach 1 here. And the last one is a really tough one. We're going to have to take out our calculator, and we're going to have to graph the function. And you're going to see that it's undefined, obviously, at negative 5. That's some kind of removable discontinuity, though, which means the limit at -5 might exist. It's a little bit of a grapher error here too. This should continue, I believe. Not 100% sure, but what we can do is we can go to second table set. And we can start our table at -5, where the point we're looking for, and we'll go by a small increment. Like I'll go by 0.01s here and take a look at that table. And now what you'll notice is that right around, -5, it's right around -7 on both ends. It's approaching -7. You can see from the table, and you can go back to table set and you can make these increment as small as you want. It's just going to give you more accurate information, really. But oops, I'd have to start my table at -5 in this case, and then what you'll notice is right around this point, it's really, really close to 7 on both sides, -7. So if you try -7, that's the point we're looking for. That's the limit as x approaches -5. And I accidentally entered in the same problem twice there. Sorry about that. Just enter the answers back in for 13. The next one, same thing. We're going to have to do this within the calculator because if we plug in 7, I get undefined. So what I do is go to second table set. I'm going to start my table at 7, and I'm going to go by 0.0001. You can go by a really small amount. That way when you look at your table, you get a really accurate idea of what's happening exactly around it. So right around it, just above 7 is 0.16 repeating, and just below 7 is 0.16 repeating. Therefore, the limit is 0.16 repeating. Okay, the next problem, the hard part, is drawing the graphs, the piecewise function. I usually just use points, so plug in like -1 into the first function, you get -6. It's defined there, and then think about, okay, well, this is a line with a slope of 1, so we don't want to graph the line, we want to graph just the left of that, so I draw an arrow down to the left, and so on. So just keep, plug in points and think about what it looks like, and you get this graph, for me anyway. And so then as x approaches -1, from the left, we get -6. As x approaches -1 from the right, I get 2 here, right up here. And then as x approaches -1 overall, then that has to be undefined because they're two different numbers. As x approaches 1, though, that is defined because it's the same from the left and the right. It's approaching 2. And then f of -1 is -6 down here. Okay, the next problem right here, it helps to graph it. Then you can answer these questions. As x approaches -4 from the left, it's going up to positive infinity, INF. As x approaches -4 from the right, it's going down to negative infinity. As x approaches 4 from the left, it's going down to negative infinity. As x approaches 4 from the right, it's going up to positive infinity. And then as x approaches negative infinity, the function looks like it's going to 0, but we would take the ratio of the leading coefficients here to find the horizontal asymptote, which is actually 1. And that's going to be the case for as we approach negative infinity and positive infinity. And the last problem, 17, I'm going to make extra credit. Won't ask you one that's difficult, so let's just make this extra credit for now.